Alright, so we're starting this unit 11. It kind of covers 3 separate topics, which are all relatively connected. That's why we put them together. We start with a couple days of Voronoi diagrams, which is really just an application of linear functions. And then we will dive deep into vectors. If you look through the thing, there's a lot of days on vectors. And then we explore this idea of complex numbers, which we'll talk about when we get there, but that's kind of the last bit of the unit down here. But this first section talks all about Voronoi diagrams. And so here it says this diagram below shows 3 points. So we have A, B, and C. It says indicate the region in which all the points are closer to A than B. So if you were looking for every set of points that's closer than A to B, you would find the midpoint between A and B, which we can see is this point here. And so anything above that red line is closer to A, anything below the red line is closer to B. So this is closer to A than B is any point above the line y equals 4. So then it says do a similar thing for A to C. So how do you figure out if it's closer to A than it is to C? Well, the point's exactly halfway between A and C. So A is at 2, C is at 8, so at, what would that be? 6, 3, 5, right? So at 5, right, anything to the right of this line is closer to A, anything to the left is, anything to the right is closer to C, anything to the left is closer to A. So this is, A is closer to C is when we have, it's to the left, any point left of the line x equals 5, right? Vertical lines, x equals y equals horizontal lines. So then closer to B than C, right? And so this one's not as easy to figure out, right? Like you might have to do some calculations for looking at it. Between B and C, the actual midpoint is right there, right? We could calculate it, and we will eventually, but just for the purposes of looking at it, that's the midpoint. And then it would be a line that is through here. Right? And so the way that we will end up finding it is realizing that it's the line that's perpendicular to BC. And so anything kind of, we can think of it as above this line, right, whatever it is, anything above this line is closer to C, anything below this line is closer to B. And so then it says, we don't need to find the equation line, we could say any point closer to B would be any point below the, what's called perpendicular bisector, right, the line that is both perpendicular and bisects BC. Right, so if I was to draw BC, perpendicular bisector is this one that I'm about to highlight, that. Right, it's perpendicular to BC and it cuts BC in half, perpendicular bisector. So then it says, hence shade the regions for all the points that are closer to A, B, and C. So we can kind of see how this will work. We can essentially remove some of these lines, and it might be easier to just redraw it and say, we notice that they all converged at this point. Anything above there splits A and C. Anything over here, anything, in this direction, split A and B. And then B and C were split in this way. And so we can see that anything that's over here is closer to C. Anything that's over here is closer to A. And anything that's down here is closer to B. Right? Anything that happens on those lines, right, on these lines that are creating these boundaries, is equidistant from the points that it's closest to. It kind of says, what do you notice? Well, this creates a diagram that shows the closest points to each, and we'll learn this word eventually, site. Right? A, B, and C are called the sites, and then they make the region that they're in the points that are in those regions are closest to each of those sites. This is an example of a Voronoi diagram. Right? Voronoi diagram is just a diagram that has multiple sites. We'll kind of define all these words down here. Yeah, so let's take a look at these definitions. So a Voronoi diagram divides a plane into regions called cells, right? So if we go back up here and label certain things, the cells are the full region. This is a cell, this is a cell, and this is a cell, right? So we have cells. Each cell shows all the points closer to a particular point in the cell called the site. Right? So a site, right? Our sites are C, B, and A. Right? Those are all of our sites. The boundaries of each region are called the edges. So those are the perpendicular bisector. Right? So the edges, right over here, edges are that, and that one. Okay, 3 edges making up this one. And the point where they all meet, and sometimes it's more than one. In this case, it was a single vertex or vertices. And so in this case, there is one vertex, and it exists right there. Right, that's the vertex where all the cells meet. Right, so we have these words to be able to talk about the vocabulary that goes around these diagrams. Here it says all vertices are at the intersection of 3 edges. Right, so where 3 edges meet makes a vertex, and there could be more than one in an image. Yeah, the edges lie along the perpendicular bisectors of the line joining 2 cells. Right, so if I join sites, the line joining 2 cells. So the edges, right, like this edge right here, is the perpendicular bisector and joins the cell that contains A and the cell that contains C. So making Voronoi diagrams, you can be asked to construct one on your own, kind of like we just did in that first example, right? That was a construction of a Voronoi diagram. That was a relatively simple one. Sometimes it can be more challenging. It's not always easy to draw a Voronoi though. For example, if you look at this one has just 4 sites, right? There's, you can see the sites A, B, C, and D. Okay, we have sites A, B, C, D, and C. Here it says, can you find the correct regions with just 4 vertices on the diagram below, which show all the perpendicular bisectors? And it's kind of hard to do, right? So it's like saying, well, is it this? Is that what I'm shading? Or is it, where do I have to cut it off? What's closer to A? Well, is this part actually closer to A? So that's everything that's D, right? It can become really challenging when you have lots of them. So there is a way to do it instead of looking at all the lines kind of all at once. You can add one site at a time and gradually build up the diagram. And so this is called the incremental algorithm. So instead of starting with 4 sites, you could maybe start with 2, build that diagram, add a 3rd site, build that diagram, add a 4th site, and build it off of that. Let's take a look at an example. For example, there are 4 fire stations. So we have these fire stations A, B, C, and D in a town. The coordinates of the fire stations are given here for A, B, C, and D. In order to improve the response time, the township has installed a new centralized fire response system, which allows a dispatcher to send a fire truck from the nearest fire station to the location of the fire. And so then it's asking, how should the township be divided into areas so that there's one fire station at each area, and this fire station is the closest one for each house in that section. This is basically telling you to build a Voronoi diagram with sites A, B, C, and D. Right, and so we're going to do it over here, right? So on the next page, it has these points, right? And so it had the point A1, was 1, 4. B, just for reference, was 1, 0. C is 5, 1. And D is 4, 3. So it says draw the perpendicular bisector between A and B and gently shade those points nearest to A. Right, so it's basically saying, okay, well, let's ignore these two and just draw the Voronoi diagram between A and B. And so that gives us, this is at a y value of 0, this one's at a y value of 4, so it would just be a horizontal line at 2. And then it says we'll shade everything closer to A. So in reality, we'd be doing this. And then that shows me, okay, right now I have a diagram that shows me everything closer to A than it is to B. Yeah. So then it says find the equation of the perpendicular bisector of AC and BC and add these to the diagram. So if I was to connect AC and find its perpendicular bisector and BC and find its perpendicular bisector, I then want to draw those. And so this requires us to remember some things about lines. So if I want to find the perpendicular bisector of AC, we'll start with that one. I first need to find the slope of AC itself, right? So A to C, A is 1, 4, C is 5, 1. So the slope of AC is 1 minus 4 over 5 minus 1. So it's a -3 over 4. So that's the slope of AC. But we want the line, we don't want the slope of AC, right? We don't actually want that. We want the one that's perpendicular to that. And so that's going to be the perpendicular, right? This is the symbol for perpendicular. Slope is positive 4/3, right? Flip the opposite reciprocal for perpendicular, right? Flip it and make it the opposite sign it was. And then the other thing I need is a point. And the only point that I could figure out is the midpoint of AC, right? Like that I have the perpendicular part, but I need the bisector part. And so I, again, could use the points and find the midpoint. So 1, 4, and 5, 1. So if I want the midpoint of AC, it's going to be the average of the x's, 1 plus 5, divided by 2, comma, the average of the y's, 4 plus 1, divided by 2. And so that would be at 3, comma, 2.5 is where that midpoint is. So I can start to draw that. And maybe I'll remove the shading. So I can draw 3, comma, 2.5 is my midpoint. And then I have a slope. So my equation is y equals, y minus 2.5 equals 4 over 3 times x minus 3. If I write it in point slope form, right, that could be my equation. I could rearrange it to write it in a different way, but really I just need the point, which I can start at the midpoint, 3, 2.5, and then use my slope. So I go up 4, right 3. So I go up 4, but remembering each of these is a half. So up 4 would be 6.5, but that's too far to go up. So I could do up 4, right 3, but I could also do up 2, right 1.5. If I half everything, it's still the same ratio. So I could go up 2. That would be up 1 is there, up 2 is there, and right 1.5. So that's right 1, that's right 1.5. Is there. And I could do the same thing. I could go down 2, so down 1, 2, and left 1.5. Right, so I end up with this line. trying to draw it as accurate as I can. So then I need to do a similar thing and find the perpendicular bisector of BC. Right, so maybe pause the video, see if you can do it on your own. Right, so the slope of BC, C to be 1 minus 0 over 5 minus 1, which is 1/4. So the perpendicular slope is -4. And I need the midpoint of BC. And so the average of the x is 5 plus 1 divided by 2. And 0 plus 1 divided by 2. And so that's 3, 0.5. Okay, so I should graph that. 3 and 0.5 is there. And this one's going to have a slope of what was the slope? -4. So it goes, it's technically -4 over 1. So you could say it goes down 4, up right 1, or up 4, left 1. I think that's going to be easier with what I currently have. So that's what I'm going to do. I'm going to go up 4, left 1. So up 4 brings me 1, 2, 3, 4 up there, and left 1 brings me there. So if I connect those, let's see, start to build this, and that one. Okay. And so I've now kind of added a decent amount of the perpendicular bisectors. Right, so we've seen that I've added, for example, if I have 4 vertices, I need the perpendicular bisectors between AB, I need between AC, I need between AD, and then I need between BC, BD, and what am I missing? CD. Right, so the ones I already have drawn, I did between A and B, that was the first one. I drew between B and C, and I drew between A and C, yeah, that was the one I just drew. Right, so I've drawn 3 of the 6, right, like I'd still have to find AD, I'd still have to find DC, I'd still have to find the one between B, D, yeah, I haven't done that one either. So it kind of goes on to explain how the incremental algorithm works. We're not going to do it for the whole thing, but you can kind of see even just from these, if I was to start to remove some things, so let me change my eraser. Right, if I start to remove some things, like it's pretty obvious I would get rid of this whole portion of it, because that's everything closer to A. Right, I would remove this whole portion of it because everything in there is going to be closer to B. Right, and I could start to see it forming, right, these things, but again, this is not all of it, right? So I can start to see the cells that exist. Like I have this, right? But I'm clearly missing kind of what happens between A and D, right? There's another one that would cut this cell to be a little bit different. And so it gets to be a bit tricky when you have a lot of different cells, right? And you have to build it. So the incremental algorithm kind of works like this, right? This is what it says. It says begin with a perpendicular bisector which lies in the new site C, and then keep going. So you keep moving, move along the line until you reach an intersection with another perpendicular bisector between the new site. And then that will also be the boundary of a previous Voronoi diagram. Leave the intersection along this other perpendicular bisector in the direction that lies entirely in the cell around another one of the sites. And basically end up with these polygons, right? These shapes, these convex polygons. And then you'll kind of like repeat it again. And then once you've done it for all of them, you'll end up with something that looks like this. You generally won't be asked to draw an entire Voronoi diagram for 4 sites. Lots of times it'll say add the line that needs to be added, like maybe you'll need to add 1 and everything else will already be there. But for the one that we were just looking at, this is what it would look like in the end. And so if you went through that whole process and kept really good track of where things were, you would end up with a Voronoi diagram like this. But again, that's not really an exam question. So yeah, right. So this is what it could end up looking like. This is a completed Voronoi diagram. And so kind of in the context of the problem, trying to understand what we could use them for, it says a few years later, a new fire station is built in the town at the point with coordinates 2, 1. So if it was, for example, to put 2, 1 here, it says use the incremental algorithm to construct a new Voronoi diagram showing the areas served by each of the new fire stations, right? And so, what letter are we on? A, B, C, D, E, right? You would then have to go figure out, okay, well, what's the perpendicular bisector here? And I would draw it until I hit another one of the points of the cell. And then what's the perpendicular bisector between A and E? Well, A and E has a midpoint approximately there, and its perpendicular one would be there, so I'd start to draw things like that. Right, those would be closer to E, and then I would draw between E and C. Its midpoint is there, and I would draw until I hit another portion of the Voronoi that already exists. Then E and D, its midpoint is maybe there, right? Like I could find it more accurately by actually doing it. And I would end up with a shape that kind of looks like this. These would continue down here until they intersect, right? Like down like that. And so then I would realize, okay, well, everything now inside of this kind of shape in the middle belongs to E, and I've removed the other parts that maybe belonged before to D. So now this new area kind of in the middle, it belongs to E, and it's shrunk the areas of all the other ones, taken a piece of all of those. Yeah, so then kind of the last part to talk about is just this nearest neighbor interpolation. It says each site is assigned a numerical value, such as the amount of rainfall that fell on a particular day or level of pollutant. Then the value of all points in each of the site's cells is assumed to equal that value. So for example, if this, instead of being fire station, represented different amounts of rainfall, like up here they had 2 millimeters, over here they had 10 millimeters, here they had 5 millimeters, and over here they had 3 millimeters, right? Like, so they had rain gauges that were measuring rain at each of these sites. Right, if they said, well, I'm somebody who lives at 3, 2, I live here, how much rain fell at my house? Well, you would just take the value that is that of your site, no matter where it falls. So if I lived at 0.5, 2.5, I'd say, well, I would expect 2 millimeters of rain. Right, that's this nearest neighbor interpolation. Right, like the fact that I'm closest to each of these sites, whichever site I'm closest to is the value that I would then take. So that's what this one is saying. For some ease for your homework, you can do it in here, right? Like we provided you some of the grids so that you can kind of just do them in here without having to draw them kind of by freehand. So make sure you get a chance to try some of that homework and practice building these Voronoi diagrams.